3-page deal, and we did the first couple the other day, and now we're ready for number 11. So we're going to find the average rate of change.
Oh, did you start? Did you just start the video?
Yep.
Oh, okay.
All right. So, yeah. So here we go. So what's the first thing I need to write down?
-1.
I need to write f of -1 minus f of -2 over -1 minus -2, right? That is going to be my average rate of change. Since they gave me an equation, I can evaluate f of -1, right? So f of -1 will be -1 cubed plus 3 times -1. Now do this carefully. You guys are all smart people, but if you try to do too much too fast, you might lose a negative or something somewhere. So I'm putting in -1 cubing it. So what's this? -1, but it's -1, so it's actually 1 minus 3. So f of -1 is -2. Right? Okay, and then I'm going to find f of -2, doing the same thing. So negative, you with us? Yeah, you're with us, but you're on the wrong page. We're right here. So what do I get when I put in -2? I get -2 cubed plus 3 times. Okay, so this right here is going to be 8. Did you get 2? It looks like the denominator is 1. So did you get -4? Now, since this is not a word problem and there's no context at all, the answer is -4. But often on average rates of change, we need a unit, like dollars per minute or something, right? Depending on the context of the problem. All right, B, same thing. G of 3 minus G of -1 over 3 minus -1. So this is what we are starting with, and we're going to write that down every single time. Now, look at your graph. What's G of 3? 4. What's G of -1?
0.
So it looks like 1. And again, no context here, so no unit necessary, but average rates of change are something per something. All right, table above, find the average rate of change. So we're going to do A of, we're going to 2,000, so A of 2,000 minus A of 1850. Over 2,000 minus 1850. Is that okay with everyone? Now we're using a chart. So what's A of 2,000? 81.83 minus 46.10 over 150. How does that look? Does that look okay? Who signed that?
This is Carver.
Okay. Did you get 0.2382?
Yeah.
Now, does this problem have a context? Yep. So what will be our unit? This one's a little bit tricky. So 0.2382 age years, or I don't know what else to call it, per year, elapsed year or something. Because both of these units are years in the chart, would you agree? It's age over like a year. So we can't really say years per year, so I'll say years of age per elapsed years of time, something along those lines. Is that okay? All right. Selected values are given below. For each value, determine if it could be linear, quadratic, or neither. And I'm going to add, explain your answer. Because we're okay with the math, but some of us are really messing up, losing points on our explanations, on our units, on that kind of stuff. So, here we go. What do you think about that first one? A. Linear, quadratic, or neither? Be really careful. What is tricky about this one? These aren't the same. So the only conclusion you can draw will be if the average rates of change are the same, you can say it's linear. Otherwise, you're not going to be able to make a conclusion. So, what is our average rate of change here? For the first two data points, the average rate of change would be 1. For these, it would be 3/2, and for these, it would be 5/3. So our conclusion is, we don't have a clue. We don't know. How about B? This one's okay though, because what's our average rate of change? 1. So that one is linear. That one is linear. Remember, you can't look at the differences and make a conclusion if these aren't evenly spaced. So in the last one, they are evenly spaced. What do you notice about those differences? They're linear. So you will say this is quadratic data. And you will you'll explain that either with the second differences are the same. That's good. Or you could say the first differences are linear. That means they're going up or down by the same amount. So our first differences are linear. That would be one reason you could use. Or you could go ahead and do the second differences and say the second differences are the same. And of course, all that's predicated on the input intervals are equal. That has to be the case. Okay. 13. We're going to solve this guy. Any ideas on how we might solve that? Does it factor by grouping?
Take out a 2 first and then factor by group.
2x squared.
Take out a 2x squared. Oh, somebody said, I heard somebody say, take a 2 out of the whole shebang. Perfectly legit. It's going to come out at one point, either now or later. That's absolutely okay to do that. I've already got this written down, so I'm going to go ahead and do this. but that 2 is going to come out. And it can come out right off the bat. You have a GCF, you can just take it out right now, if you want. I didn't take it out, so now look what I've got here. What do I got here? Now I'm gonna have to take that 2 out. I'm gonna have to put it out here in front. And that'll leave me with x squared minus 4. Which factors into the difference of squares. Alright, how do we feel about that? Did everyone keep up with all that? You may have done things in a little bit different order, and that's okay, but this is how we should all be ending up, right here. So here's my number line. I've got -2, 2, and 5. Remember, only the x's get dots on the number line. Only the x's can be zeros. So that 2 is there and it's fine, but it doesn't get a 0. There's no dot for that. There's just dots for the x's. And those dots would all be closed in, right? And now we're going to do our sign chart. We're going to show our work. True response question. We're going to show all of our work. So we pick a number, any number you want, plug it in here and see what happens. So, you go ahead, I'm just doing it, you do it. Anybody have a question about that? Ellis, your hand up? Nope. You all good? Okie dokie. Determine the degree of the polynomials represented in the tables below. Okay. Do you remember? This is so cool. That if the first differences are the same, your data is linear. If the second differences are the same, it's quadratic. If the third differences are the same, it's cubic. So assuming that your input intervals are all evenly spaced, which they are in both examples, you're just going to go through until you find the differences that match. So keep working on that while I put attendance in, and tell me what you come up with. What'd you come up with? First one's quadratic, because the second difference is matched. And how about B? Cubic, because we had to go all the way to the third differences, and they matched. Everybody fine with that? All right, 15 more tables. For each function, determine if it could be concave up, concave down, or neither. Okay, wait a second. How do we determine if it's concave up or down? Declan?
Look at the changes in the rates of change.
Okay, so the rate of change. We gotta look at the rates of change. And what does it mean if the rates of change are increasing? We're concave up? And otherwise, negative or decreasing, we're concave down. All right, so let's see what's happening there. Did you notice all your input intervals are equal? That's great news. Here's some ideas. What anybody have an idea for A? Or concave up, concave down, or neither? What's your thought on that? Concave up. Concave up because the rates of change are increasing. Would everybody agree with that? They're negative, but they're getting smaller negative. That means they're increasing. Very good. Concave up. What about B? Neither one. What's going on in B? It's linear. No concavity. It's not look at average rates of change are constant. Perfect. And what about C? Concave down, because what's happening to the rates of change? They are decreasing. Everybody good? All right, 16, we need a calculator. Before we get our calculator out though, let's make sure we understand what's going on. Number of cars can be modeled by this function. At what time does the number of cars change from increasing to decreasing? Okay, now I want you to think about that for a second. At what time does the number of cars change from increasing to decreasing? What would we be looking for if we're changing? Think about what that picture looks like. We're going from increasing to decreasing. What does that mean we're looking for? A maximum. Does that make sense to everybody? That you're looking for a maximum? All right, so let's sketch it. See if we can figure that out. Come up with something
2.446 hours.
after 2.446 hours. Everybody come up with that? 2.446 hours. I hope when you saw T between 0 and 3, that you set X min at 0 and X max at 3. Because that's all you're allowed to look at, is just that part of the picture. That's your domain. Okay, 2.446 hours. Good. All right, last one, number 17. On each interval, determine if the rate of change is increasing or decreasing. All right, so wait a second, process that. We just talked about it. If the rate of change is increasing, we are concave up. All right, so let's look at from 3 to 4. From where X is 3 to where X is 4, would you say that's concave up? Yep, so that is increasing. A is increasing. How about from -4 to -3? Decreasing. Oh no, increasing. That's still concave up, isn't it? Yeah, that's still increasing. Concave up from -4 to -3. Rate of change. All right. On each interval, determine if the function is increasing or decreasing. So what's happening from 2 to 3? Would you say that function is increasing or decreasing? Increasing. Because if the function is increasing, what are we looking for? Are we going up or down? Okay, that's the function, the y values. All right, how about -3 to -1? Neither, it's doing both, right? Part of it is decreasing and part of it is increasing because we have a minimum in between there. Right, so B would be neither or both. It isn't increasing or decreasing. Part of it is increasing, part of it is decreasing. Okay, is that all right? All right, let's take a look at anything from homework that you have questions about. Any homework papers that you've gotten back that we
Homework.
need to look at.
2.2 is question 3.
2.2, question 3. So I need to go back and figure out what's going on with A. So find A. What is it? I need to go back. Find A's length increases by 50 feet per day. And find B's length, the length of each line is 10 feet when we start. So, find A. Okay, so let's look at what line A is doing. Line A is 10 feet at the beginning. This is like A sub 0. This is after no time at all. That's the beginning. And then every day it increases by 50. So after one day, it would be 60. Would you agree with that? And after 2 days, it would be 110 and so on. So I'm gonna write an equation for that, okay? And I've gotta be really, really careful because this is the initial amount. This is after no days. So if I build my equation like this, 10 plus 50, if I put n minus 1, I'm in trouble. Because this isn't the first term, right? So I'm gonna say this. So if n is 1, after the first day, I get 60. Does that make sense to everybody? You gotta be really careful about what you use as your first term and then how you interpret the exponent. So this would be after n day, not the exponent, the variable. So that would be after n days. Does that fit? Okay, so that's vine A. Now, what is vine B doing? Vine B grows by 5% a day. So it started out as 10 at the very beginning, before any days, very beginning. And then it is increasing by 5%. So in other words, after one day, it would be 10 times 1.05. Okay, now what's the question? Will B ever be longer than A? If so, when? Okay, so basically, what do I need to know? Will this guy right here ever be bigger than this right here? Do you have a gut feeling? What's your gut feeling? Yeah? Because which is over time, which is always going to grow faster. Exponential, geometric. Yep. Yep. This is always going to grow faster. Now, over time, it's going to take it a while to catch up. But this is linear. This is maintaining a constant increase. What's this one do? Shooting up? So, I'm going to use my calculator and try to figure that out. Now remember, it's going to take some time. 10 times 1. Yes. And 10 plus. The window's going to have to be bigger than 0 to 3. Okay. The window I ultimately used was 0 to 300 on the X's and 0 to 20,000 on the Y's. There are lots of windows you could use, but that gives me a great picture. I see my line and I see my exponential, and so I'm going to find that point right there. So. So I got that point right there to be 133.295, comma 6674.771. Anybody else get that point? Okay, now remember the way I set up my equations, you guys. Remember, this was on the X day. So remember, on day one, it was 60, or after day one, it was 60. After day one, it was 10 times 1.05. So my X is the day. So when are they equal? They're equal on sometime in the middle of the 133rd day. So on what day will B actually be taller than A? The 134th day will be the first day. Now, some of you used exponents like this, and that's okay. But understand that doesn't work with the numbers that you've got, because the first time you multiply by 1.05 is at the end of the first day. So that 1.05 is the first day. And that 50 is the first day. Okay, all right, got it? Perfect. Anybody else?
On the same homework, can you do number 6?
The jumper I wanna buy costs $10.50. If it goes on sale each day for an additional 50% off, after how many days will it cost less than 100? I have a feeling this might be the same kind of mistake. So, what is the 10.50? 10.50, is that after any days at all? No. So if I want to know how much it is after day one, I'm going to take that 10.50 and multiply it by 0.85. So 1.85 is 1 day. So if I want to know, I want to know how many days it's going to take to cost less than $1. So I need 10.50 times 0.85 to some number of days. 1 day, 2 days, 3 days to be less than $1. This right here is the price of the dress after 1 day. So this will be the price of the dress after X days. Okay, so I can do the same thing there. Use that for the window. So this time, obviously, you're gonna get an exponential that's decreasing, and here's your line, and you're looking for that point. And it looks like that point is 14.468, comma 1. So what's the question? After how many days will it be less than 100? Well, this, or less than $1. This is sometime in the 14th day is when it actually gets to $1. So it'll be the 15th day when it's less than $1. When you build your equation, guys, and there are other equations you can build. When you build it, make sure that it gives you the right term. So, you see what I mean? When you plug in 3, make sure you're getting the third day. Or whatever it is.
So with this rate value, I mean, it's like you started with this, that's the initial value,
Yep.
not the first.
That is the initial value. That's exactly right. That is your y-intercept times 0. All right, anything else? We've got Sophia,
Can you do number 7 on 2.1?
2.1. Number 7. With each stroke of the pump, 10% of the air is removed. How many strokes are you required to have less than 20% of the air remaining in the tank? Okay, so my initial, I'm starting with a full tank. So my initial term will be 1. And every time I pump the thing, I remove 10%, which means how much is left? 90%? Question doesn't say how much to be removed. It says I want to have 20% remaining. So after 1 stroke, I have 90% remaining. So 1 stroke would be 0.9, 2 strokes would be 0.9, and so on and so on. And I want that to be, I want to know when that equals 20%. So you can do this the way I did these last two. You can do it by graphing and finding out where it intersects. You would also do logarithms. So if you take the logarithm of both sides and divide the log of 0.2 over the log of 0.9, let's see what that is. That is 15.2756 or so. So what does that mean? What does that number right there mean? That number means that I have every pump is an X. So 1 pump, 2 pumps, 3 pumps. So I have to pump it 15 point sometimes to make it exactly equal 0.2. So when is it going to be less than that? 60. All right, anybody else?
Do you get number 4 on 2.2?
2.2, number 4. Number of people sick with the flu, can be modified to genetic sequence. 18 sick on day 2, 217, okay, so we got a geometric sequence. And this is 18, this is day 2. This would be day 1. And then I know day 7, so there's day 1, 2, 3, and day 7 is 217. How many will be sick on day 10? Okay. Well, one way to do this, we said day 2 was 18 and day 7 was 217. This is geometric. So how many multiplications is it going to take me to get from the second term to the 7th term? 5. And those are multiplications. So I'm going to times R, times R, times R, times R, right? 5 times. And the total multiplication is going to be whatever 217 divided by 18 is, and it probably isn't anything good. No, it's not. So I'll just leave it that way. So the total thing I have to multiply by is 217 over 18. Does that make sense to everyone? And I got to do that in 5 steps. So my ratio is going to be the 5th root of that. Now, I don't like messing around with my nth root button, so I'm going to do 217 over 18 raised to the 0.2 power, the 1/5 power. But you do have an nth root button in your math menu, so you can use that button if you want. You have to press 5 and then the nth root, and then 217 over 18 equals. Okay, so this is going to be some decimal, and that's okay. I'm going to hang on to that for a second. That's going to be the thing that I keep multiplying by to work my way down the line. Now, I need the 10th one. So there are different ways I can do this, but could I start here and multiply by R cubed? So I'm going to take 217 times this thing, and I'm going to cube that. And that should give me my answer. So let's see. Okay, I got 966.434. Now round off with exponentials is bad, because they change so fast. So try not to round off. So I notice I didn't type this in and get a number, I just left it, and then I typed it in to get my final answer. So what's the question say? What question am I on?
4.
To the nearest whole number, how many will be sick? 966 people will be sick. All right, what else? Declan, you kept raising your hand and I was ignoring it. What, do you have one? We got it? Okay. Anything else? Let's see, what did,
We do 11 on 2.3.
2.3, number 11. 2.3, number 11, asks what is the domain of an exponential? So what does this look like? We should know what that looks like. Doesn't that look like this? I want to know about the domain. Those are the x values. Tell me about my x values. How far left? How far right? All of them. Right? All of them. Some people miss, I can't remember if we already talked about this or not, but number 5 on that 2.3, some of us missed that. There's a lot going on in the problem. And you're going to determine the end behavior. And I think a picture helps. So I'm going to start right here. What happens when we take 2 to a negative power? It becomes 1/2. So this is 1/2 to the x. Now what does 1/2 to the x look like? Decay. So this part of the problem right here looks like that. Now what happens when you put a negative out in front of that? It turns it upside down. So now it looks like this. So on the left, negative infinity. On the right, 0 from the bottom. The size of your initial value doesn't really matter. So that's going to stretch your picture, but it's not going to change your end behavior at all. The negative here and the negative there is going to change your end behavior. Okay? All right? Anything else from those homework? Yep.
Maybe number 4, 2.3.
2.3, number 4. Same kind of thing. We're going to start by dealing with this negative exponent. Aubrey, none of your, when we talk about an exponential function, my power is x, okay, not negative x. So I need to change that. So this would become 5 to the x, because a negative exponent flips your fraction, right? So what's that? That's exponential growth. Yeah, so that's going to look like this. So on the left, it's 0 from the top, and on the right, it is infinity.
Well, number 5 would like flip the 4, so would that be growth?
Growth.
Okay.
Yep, the y's are getting bigger. Now, they happen to be negative. We're not going to see that in the real world. Like if our vines are growing, we're not going to see this picture because those y's are negative. But yeah, that's a growth. Ultimately, that's a growth. All right, anything else? Well, bless Mr. Passwater's heart. He has some extra stuff he's created. And I'm just giving you this for your own practice.
Mr. Password, I'll autograph my book.
Mr. Password.
Hmm?
We will never know who's Mr. Password.
And calculus. Those of you that take calculus next year will continue to use Mr. Passwater's stuff.
Really?
We're just a bunch of thieves over here. We always steal all his stuff. All right.
What is the base?
So, I'm not assigning this.
Base this?
I don't care. I mean, let's not throw it in the hallway. If you don't want it, put it in the recycle. But it's just some extra stuff for you to do and compare with each other. You might want to do one from each